Okay. I don't know why I'm so obsessed with this Fourier transform, but I've been taking notes on it for like weeks, and I paid for this class on Coursera to study um signal processing, just because I was like, like I could deepen my knowledge on some tech skills, and I just kind of wanted to rant a little bit about the Fourier transform and just everything that I've learned from signal processing thus far, while also taking care of canceling some stuff. Um, so. The Fourier transform is a signal um, is an algorithm used to process signals inputs into a computer. And the class started by talking about um, like transatlantic cables, basic linear algebra, um, and let's see, I have maybe my notes are here. Ugh. Okay. Okay. So these are my notes on the discrete Fourier transform, and um, also some doodles and sketches. And they can be complex to read, but this is just an example of what the Fourier transform can look like. In general, you're going to want to, when you're plotting data or numbers on a grid, you're going to want to start with a grid. And you can use a computer for this, or you can like hand draw a grid. So to start from the beginning, we have a blank page, and this is sort of like your x-axis. So you might have variable x going across a linear plane, and then variable y going across a vertical plane. And then you have a grid, essentially. From variable x equals 0. Oh, come in. Hey. Yes, I sure can. Okay, so you have variable x, which is your x-axis. It's a horizontal plane. And then you have variable y, which is your vertical axis. And at 0, 0, x equals 0, and then y equals 0, you have this point right here. And anytime a data, numbers, or a signal moves across either of these planes, and we typically use the x plane to describe, say, like time in hours. You could have hours. Or the y plane to be, actually, I would put time across the y plane, and then you might put like frequency. Actually, let's put frequency as our y, and then hours as our time here. And time, we either use a lowercase t, capital T, capital N, or lowercase n to describe time. In some algorithms, you'll see like when you're describing like interest, I think you might have like variable a squared plus t, and then, or like 2t, and then you would use, say you had 2t, so you have variable 0, 2t, whatever your time equals, if t equals 2, so you have 2 squared, basically, which would give you 4, 2 squared. But we tend to use like the variable, like variable t, to represent an undefined amount of time. And so we put that on the x horizontal axis, and then we might have frequency y going across the vertical axis. So if you have a signal processed at 1 point, let's say at 1 on the axis, and it's received at a frequency of let's say like 10 hertz. You can even make this decibels. At 0.1, the frequency processes at 10 hertz. So you have a signal processed here. And the way a wave length is described, or the way a wave is formed, is when you receive more than one signal. So if you have 0.1 and then you have 0.2, say 0.1 is where the x and the y axis meet, and then 0.2, another signal is received. Let's say it's at 15 hertz this time. You can just chart that. And then suddenly you've got 2 points in your grid processed at different times. And so if we chart from 0 up to our first point and then to our second point, we can do this linearly, which means it's just going to continue in a straight, rigid line. Or we can do this through sine waves and cosine waves. Sine and cosine. And to explain sine and cosine, you're going to want to know about pi. And pi, which looks like this, and is equal to about 3.14159. That's about pi, and so on. Pi represents the circumference of a circle. So it looks like that. It represents the circumference of a circle, which equals pi. And in a unit circle, we split our circle into a discrete number of finite spaces and move periodically in sequences of pi. So you might have pi over 2, pi over 3, pi over 4, 2 pi, like so. And then that continues all the way around until you get back to pi. And that is how you generate a circle. And then you have a sine and a cosine wave. And quickly to explain a sine wave, we're going to go back to our linear grid. And we're going to start at 0. And then from 0, we're going to move up over the axis, dip down below 0, and come back to 0. And this is one sine wave. If we have a cosine wave, we're going to start on the same axis. We're going to start at 0, the same point, and go below the axis back to 0, and back above, finishing at the axis, 0. So you have a sine and a cosine wave. And that's pretty much it. That's pretty much it. You might know that people have been trying to solve pi for a long time, which is just a whole string of really complex numbers. Most of the time in mathematics, we use a variable, which is, so to say, an undefined number. So you might say variable or undefined. And then, of course, we know about infinity, which is an infinite, undefined variable. And then we have something that's finite. And if we define something like pi or variable t, then pi is the 3.14159, and it's considered to be a finite number. Pi is a finite number. And then you might have a variable like t, and we have a series of numbers already, like alpha, omega, I think it's like that. Can't remember. Alpha, omega, phi. Can't remember phi either. That's right, phi. Alpha, omega, phi. Alpha, omega, phi, and then theta. Alpha, omega, phi, theta. And each of these are used in different equations. So if we look at our Fourier transform, you might have a DFT of cosine omega n, cosine phi n, cosine theta n, or cosine pi n equals -1 to the square root of n to the nth power. And in math, you can define any variable or any number, and it's like Webster's dictionary. It's like creating Webster's dictionary, where you're just kind of defining an equation. And so you might come up with an equation like a hypothesis. So if you, in a hypothesis, you use if, then, because. And in math, you might use an equal sign. In math, you always want to have a summary. So you have to have a theory or a hypothesis in order to solve a math problem. So a lot of questions in math might be like, if Johnny has 1 apple, then how many apples does Johnny have? And we might consider this in a ratio. We might have a 1-to-1 ratio. But if you want to answer the question, you would say, you could write Johnny has 1 apple. And if you wanted to represent this mathematically, you would maybe write J of x equals 1. Or you might write j of x equals 1. And define them as two separate equations. So you could either define Johnny. You want to have Johnny as a separate entity. So you have Johnny. And then 1 apple equals 1 apple. But you don't want Johnny to equal the apple. So because Johnny's not the apple, and you want to know how many apples Johnny has, you'll be able to define that. So you might have J, capital J, and then in math we use parentheses or like bars like this. I don't know what they're called, brackets like this, to say of. So we have J of x, and x is used as the number of how many, because we want to answer the question. We have J of x, or J of 1, which means Johnny has 1 apple. Let's say we put this on a grid, which is to say we define it in a space and a time. So if we have a grid and we want to show Johnny on the y-axis, Johnny, and the apples on the x-axis, apples x, Johnny y, then we might say at 1 and 1, we have our point where Johnny has 1 apple. And if Johnny wants 2 apples, where does Johnny equal 2 apples? So we're going to want to plot a second apple, 2, on the same y-axis, and we're going to add an x to get 2. Now we have 2. And so on. And if you want this to continue, you could use an ellipses to define so on, or you keep it as a variable x to say that it's undefined, because we don't know how many apples Johnny will have. Let me think. So we can plot this on a grid, we can plot it on a chart, we can define an equation, we can consider a hypothesis, we can apples, Johnny wants 2 apples, where does Johnny have 2 apples? Oh, the where. So the where, in this case, we can define it on the grid. We can say Johnny has 2 axes. These are our coordinates. These are our coordinates. And in this case, where does Johnny have 2 apples? We're going to want to say when x equals 2 and y equals 1. And so you might say at 0.21, like this. And that'll define the where and the when Johnny has 2 apples. And it also defines how Johnny has 2 apples, because apples equals 2, Johnny equals 1. At 2, 1, Johnny has 2 apples. So that's pretty much it until you get into signal processing or wavelength or sines and cosines and computer science and coding. And you might know about the binary numbers, which are 0s and 1s, binary code, and this is binary code. And binary code is used to represent on and off, 0 and 1. And you might know that certain colors, like black or white, equal different numerical values. You might have 0, 0, 0, 0 to equal white, and you might have 9, 9, 9, 9, 9 to equal black. And then, of course, if you have 0, 1, 0, 0, 1, 7, 9, that might equal tangerine, tangerine hologram, I guess. Tangerine hologram, which is just a color. And a computer can read these numbers in binary and translate them into colors and also sounds and signals. So a fiber optic cable. A fiber optic cable uses light and a small sensor to translate zeros and ones into colors and signals that say on and off. And a different a light switch uses a 0. And this is used to tell the computer when to process a color or a sound. So if we return back to our sine wave, we start at 0, we go above 0, we go below 0, and we return back to 0, which both a sine wave and a cosine wave are going to do the same thing. It just depends on where you start, pretty much. So either being a sine wave or a cosine wave, and either way, your wave is going to meet back at the same point. So if we have a sine wave processed by a computer, let's say we have a series of zeros and a series of ones, and that equals, it's either going to equal on or off at a certain point. In binary, we use addition and binary codes to just add up a total number. So if we want to get 57, we have a code like 01001110. And this is just used to say when to add and when to multiply numbers. So 01100011001 11111100000. And at a certain point, these numbers are going to get multiplied to equal 57,000. From there, a computer, or let's say like an analog, you might have heard of analog record player, an analog record player or a Walkman. Just looks like this. It takes the curves or the waves in a disc that are very specifically drawn, very specific sine waves. And with a sharp needle, which is for precision, it creates a vibrato. And something like a speaker, which uses zeros and ones to communicate when to process the sound and when not to. So you might have a sine wave or a record player that reads basic sine waves essentially that's all it's doing is reading. Just reading creating a sound. And your speaker is going to do a similar thing, but with the zeros and ones. Kind of allows you to have a way to turn it on and off. So if your speaker is processing 0, it means your speaker is off. If your speaker is processing 1, it means your speaker is on. And we really don't have much of an in-between except for variable x, which is undefined. And we really want to define this variable. So we keep 0 and 1 to say it's either off or on. And that's for a computer. So a computer might equal 1. And let's say it's on. From there, we return back to our sine waves and we start at 0. And we form our first linear sine, wave, which is just a little curve, an arc, to basically demonstrate that from here on out, we'll be going to and from 0. Like so. And a computer is really smart because it knows how to read these things. A computer can also process sound out loud. So to say, it can read like we can. And it just depends on what algorithm or code you use to compute a thought or a process. And computer scientists will use zeros and ones. And programmers will use Python, Java, Excel, and generations can read these. If you want to know how to read signals, read signals. And that's pretty much it. You want to be able to process when you receive a signal. And the other concept of not processing a signal just means that the signal is kind of lost or forgotten, which is why you might have a cosine that goes backwards, and then a sine that goes forward. And if they reach a conclusion, they'll form pi. 1 pi. 4.041596, I think. And that is a complete circle. From there, there's not much else. Yeah, from there, it's just in order to conclude pi or a signal or a sine wave, all you need to do is know how to read any signals that are transmitted and then process them and be able to communicate them to a receiver. Transmission, transmitter, process, receiver. And that's the age of AI, the dawn of AI, and signal processing, knowing how to read. And that's pretty much it. That's all I wanted to talk about with the DFT. And yeah, unless there's any questions, which I'm sure there are, but now you know how to solve them. Use these things to your advantage. Don't worry about what a computer thinks, because you already have all the tools and all the answers to solve any questions you might have. So, happy computing. Good luck out there in the world. And I'll probably see you guys later. Oh, and always remember, all answers questioned and all questions answered. Good luck, you guys.